Hi, in this session we want to apply linear regression on a bit more meaningful data, that is the one which has multiple features. So for a single feature, we saw that our hypothesis function looked something like this, right? Which we also called it as best fit line, right? So our hypothesis function was mx plus c, where x was our only feature in the dataset. But now for multiple features where we have, let's say, n features, our hypothesis function will look something like this: m1 x1 plus m2 x2 till mn xn plus c, right? Of course, this time it won't be a line, but each of the individual features will still be varying linearly with our hypothesis function, that is with our output, right? Okay. So for this problem, I have already imported the data. So I am using datasets from our sklearn library itself. Within those datasets, I have a dataset named as Boston. So I am loading that Boston using this load Boston function. Dataset is something similar to a dictionary which will have its own keys. Okay. So if I see, dataset has 5 keys: data, target, feature names, description and file name. Okay. So data will contain my x, right? So x will be in that data. If I see, so this is my data. If I see the shape, it is 506 into 30, right? So here n is 13, right? So this is what my data set is from x1 till x13, right? And each of the data point will have one output variable. So if I see dataset dot target dot shape, that comes out to be 506, right? So it is a 1D array with 506 values. Okay. Now let's see what are the names of the features. So these are those 13 features. So there is another key, DESCR, which is basically the description for our dataset. Okay. So it says Boston house price dataset. Number of instances 506. So there are 506 data points, and number of attributes, that is number of features, are 13. So this is basically a data set where we are given prices of 506 houses based on 13 features. Okay, so some of those features are per capita crime rate by town. It is obvious, right, that if there is more per capita crime rate in the town, the person would be reluctant to buy the house over there. So the price would automatically be less. Similarly, there are 12 more features like RM, average number of rooms per dwelling, RAD, index of accessibility to radial highways, and many more, right? So there are total 13 features which help us to determine the price of the house. So what we want is to train a machine learning algorithm using linear regression based on those 13 features. It will be able to predict the Y, that is our price of the house. Okay. First, let me create X and Y. Next, let's split our data using model selection. Okay, so I did not use any test size, which means by automatically 25% of the data will go into testing and 75% will go into training. So out of 506 points, 379 points went into my training data. Okay, so let me import linear regression. Let's create an object. So fitting our data. I hope these steps are very clear, right? So we have already fitted our data X train and Y train on algorithm. So now we can make the predictions. So now we can calculate the score. So my training score comes out to be 0.74 and my testing score comes out to be 0.69. It's not a great score, but that's fine. Linear regression won't always guarantee you a very good score. It keeps varying depending upon data set and depending upon the problem. Okay, so last time I got a very good score when I was working with dummy data, because the data set I took so my data points were something like this. So my linear regression was able to find a line which was very close to these points. But what if in that example I took my point something similar to this? No matter how much linear regression tries, it will not be able to find a line which will be closer to all the points, right? So definitely the score won't be as good. So it actually depends on the data set, right? If linear regression is a good algorithm to be applied on that. Now let's try and plot the graph for this. Okay, so last time what we did was we plotted the graph of X versus Y, right? These were our data points. First we plotted our testing points and then we plotted our training points, and this was my best fit line. So if I had one feature, I was able to draw my graph in 2 dimensions. Now if I have 13 features, I will need 14 dimensions to draw my graph, right? So this won't be possible for us. So what we are going to do, so if this is my data set, that is x1 till xn, and this is my y actual, we have already found y predicted, right? So what is the best possible scenario for us? The best possible scenario is that each of my y actual values matches my y predicted values, right? That my algorithm is able to predict each of the value equal to its actual value, right? So what I'm going to do is I'll be predicting y actual versus y predicted, right? Y actual, or I say y test or y train, right? So those are my actual data. So I'll be predicting y actual versus y test. If each of my point matches, then each of my point will lie on this x is equal to y line, right? So each of my point will lie on x is equal to y if all are correct, right? But since in reality our algorithm won't be predicting exactly the same values, so our values might be somewhere here and there, right? So what this means, the points which are very close to the line, we are doing very well on those, right? Because if I take this point, it means that our y actual and y predicted for this value is very close. So we are doing very well on this point compared to this point, right? Because for this point, y actual and y predicted will be very different. So in this manner, we can plot this graph and visually see how well we are performing on our data, right? Okay. So I am plotting y test versus y predicted, and I will also be plotting x versus y line. Okay, let me take some x points. X is equal to 0, 50, and let me take y again 0, 50. So I have taken 2 points, that is 0, 0 and 50, 50. So I will be joining that line and I will get my x y line. X is equal to y line. Okay, so plt dot plot plt dot show. Okay, so this is the graph that I am getting, right? So this line is x is equal to y line, and these are all my testing points. So as I can see, some of the points are very close to the line, which means we are doing very well on those points, but some of the points like this one and few more, we are not doing that great on those points, right? Okay, so let's do the same thing for our training data. And I'll also have to find y predict train, so I can find it using algorithm.predict. Okay, so these are my training points. Okay, so let's do one thing. I have another data set that is low diabetes. Let's try to run the same code for that data set. So basically this is a data set of 442 diabetic patients. Output variable is a quantitative measure of the disease progression 1 year after baseline. So some of the features are age, sex, BMI, BP, and S1, S2 till S6. Okay, and let's not worry about what the features are. Okay, so scores this time not that great again, 0.50 and 0.52. And if I see the line, okay, so here is my line, 450. Okay, so these are my training points and my x is equal to y line. Similarly, let's do it for x test. Okay, so I hope now you are clear with how to apply linear regression on different data sets. So I'll see you in the next session. Thank you.